Okay, our next speaker is Mark Turner from Riverlane.
Great, thank you. It's a pleasure to be here. I'm going to talk about collaboration at Riverlane, where we've built a new hardware decoder called the Local Clustering Decoder, which we think of as a fast and adaptive hardware decoder for the surface code. So there's several things we want from a decoder, and often they're very much in tension with one another. On the one hand, we have very intensive performance targets set by the gate teleportation circuit, which sets a fundamental upper bound on what an acceptable decoding throughput is. So in a gate teleportation circuit, we do a logical measurement, we apply a classically controlled feed-forward gate, and if we can't decode at the rate we generate, the rate syndrome information is generated, then we can counter the backlog problem. But having sufficient throughput is not sufficient in itself. We need the decoding response time to be small. It's hard to give an exact quantity to what this should be. At Riverlane, we think it should be small, not tiny, roughly on the order of a quantum operation. So that's roughly how we think what the time of the decoder should be. But of course, in addition to performance, we want the decoder to improve lambda as much as possible. So lambda describes the ratio of logical error at different distances. And of course, with higher lambda, we need fewer physical qubits to realize a given logical error rate. So we want to be as accurate as possible, suppress errors as aggressively as possible while meeting the performance constraints. And finally, we want our decoders to be flexible. So there's been a range of really nice papers describing ever more complex syndrome extraction circuitry for the surface code. We want our decoder to work with all of these. And that's a challenge once you get to the level of building hardware. So the rest of this talk is about reaching a good compromise between all of these factors. So we'll consider a pernicious circuit-level noise model with leakage. We'll propose some ways of decoding this and introduce a new hardware decoder that handles it. So briefly, what is leakage? So leakage is a very damaging error that occurs when a qubit exits the computational subspace. The damage of leakage expresses itself primarily through the fact that 2-qubit gates are designed for sealed qubits. So you can end up with long correlated errors that are long-lived and non-local. And of course, leakage is silent until measurement, so it's not immediately easy to decode. So the fact that it's non-local really means that at the level of hardware decoding, we need to be able to support leakage reduction units. One of the ones we like to think about at Riverlane is this nice proposal called patch wiggling from the Google team. So leakage reduction units are of course essential, and what this leakage reduction unit does is it swaps the role of data and qubits once every 2 rounds. So we're regularly resetting all our qubits and extracting leakage. So this circuitry is non-trivial for hardware decoders because the schedule reverses every round. So the direction of the hooks reverses. So you need to be able to build complex graphs into your hardware. But of course, supporting a leakage reduction unit is essential, but not in itself sufficient. And the reason for that is when leakage is a dominant error, it can fundamentally change the rate at which we suppress errors in the distance. And that's because DO of 4 leakage errors can cause a logical error, which is obviously very different to the kind of behavior you see under a circuit-level Pauli noise model, where we are resilient up to D over 2 errors. So really, we want to be able to solve that problem at the level of the decoder, and that means the decoder has to be able to respond to really broad classes of information from the control system. So really the Achilles heel of the fact that it can be of leakage is the fact that it can be heralded. So we want that information to be going into the decoder and for the decoder to react to the full diversity of runtime events that can occur. So in our hardware decoder, we now have the ability to evolve the error model on the fly in response to runtime events. So one of the things we can do is if leakage occurs on Q1 after the 5th measurement round, then we can perform a graph refinement operation. And what that means is basically changing properties associated with the edges in red to respond to the leakage event. This is similar to a very nice paper from the IBM team, but we make a few modifications to their proposal to make it more applicable in hardware setting. So when we refine the graph, we avoid the need for new edges and still see good performance. We also find that you can update these edges to weight 0 and thereby avoid the need for weights in the first place, which is a nice simplification because weights are very expensive things to add to hardware decoders. Finally, we also pre-learn all of these graph refinement operations, which minimizes the runtime computation that we need to perform. So that's important for throughput and latency. It's worth mentioning here that there have been several papers as well in the Neuschlatum space from the Strasbourg and the Harvard group proposing similar techniques that deal with atom loss. But back to leakage, this is some of our accuracy data where we show on the y-axis the logical error rate per round against the code distance d. We study two different noise models, so one where leakage is a dominant error, one where leakage is a subdominant error. So it's hard to predict exactly which one of these noise models will characterize the large-scale fault-tolerant regime, so we study both. And then we find that when leakage is a dominant error, we are able to significantly change the gradient of error expression in the distance by applying adaptivity. So that is associated with roughly a 75% footprint reduction, a reduction in the number of physical qubits we need. It's a slightly different picture when leakage is subdominant, so when it occurs with an order of magnitude lower probability than the 2-qubit gate error rate. But using these adaptive decoding techniques is still valuable, so we still see a 20% footprint reduction in that setting. So we were very pleased with those results because they allow because we've been able to generate them on a hardware decoder. So it remains to talk a bit about what our hardware architecture is. So the local clustering decoder is a distributed implementation of the union find algorithm. So the way these distributed implementations work is they project the decoding graph onto a processing grid. And the processing grid is comprised of processing elements, each of which encapsulates a set of vertices in a local memory. There's a range of different ways in which you can do this projection. So there's been some fine grain mappings that have been proposed in the literature. This is where a processing element owns exactly one vertex in the decoding graph. So this will give you a very, very fast decoder, but it's not necessarily as scalable because it consumes a very large area on the FPGA. What we do in our work is we introduce a new coarse grain mapping, and there's related work that was developed in parallel from the Yale group. And of course, when you coarse grain your model of parallelism, you save on area and you don't necessarily pay that much of a cost in terms of throughput. So what does the local clustering decoder's processing grid look like? So that's shown here. This is a single time slice of the error model from a distance 5 rotated surface code. And we establish a grid of processing elements where each processing element owns d over 2 vertices in the decoding graph. And where a vertex in a processing element is connected by an edge to a vertex in another processing element, we establish bidirectional links between processing elements that allow for communication while the algorithm runs in parallel. So, of course, there are some steps in the algorithm where all processing elements can execute in parallel at the same time, for example, while we're growing clusters. But there are other stages where processing elements need to communicate with one another. And in that setting, we require some higher level of control in our processing grid. So that's what these parts are for. So there are further partitioning over our processing elements. And then there are stages in the algorithm where P's need to communicate, and then we can parallelize over parts and execute P's within each part serially. And this avoids contention. So as I said, that was looking at a single time slice of the decoding graph and its projection onto the processing grid. We can extend that in 3D using in the way that's shown here, where we reproduce this processing grid for each round of syndrome extraction that the decoder is interested in that window. And then we instantiate, again, bidirectional links that account for hook and time-like relationships between processing elements. So you'll notice here that the parts have been extended a bit in the temporal dimension, so that's to account for new areas of contention that emerge. And you'll see that hook edges reverse every round to support the leakage reduction unit that we talked about at the start of the presentation. So finally, this is a slide showing the throughput of our hardware decoder. So with a relatively coarse grain mapping, we can instantiate our decoder using less than 10% of the resources on a high-end FPGA, which means we can also run our decoder at a very high frequency, so 285 megahertz. This gives us a per round decoding time that's well below 1 microsecond, and it has sublinear scaling in the distance that's quite different to traditional union find, which scales something like d² per round. So that's the local clustering decoder. We think it's fast, it's heading in the right direction for accuracy and flexibility. There's ongoing work, of course, that includes extending this to be able to handle correlations that appear as Y errors in the decoding graph. Of course, we'll be showing streaming and lattice surgery in future. Thank you very much.
We have time for a quick question. Have you thought about how, I know it's mainly a decoding talk, but you change the edges based upon how, if you can detect leakage or not. Have you thought about how in a protocol, how often you try to do that? There are different mechanisms you could use.
Right, yes. So I think that's informed by whenever we measure a qubit, then we have the opportunity to apply a graph refinement operation, and I think we would in every case. Yeah. I think, yeah, the particular leakage reduction unit we use doesn't introduce more measurements. So it's, yeah, it's the same as the syndrome extraction circuitry, the normal surface code in that sense.
Let's thank the speaker. Can we have the next speaker come up?